Hey everybody, today I'm doing my first multivariable calculus video. So before we start this video, you should be knowledgeable about single variable calculus, and some knowledge about partial derivatives and gradient and vectors should also help. So not required, but it's best to. And if you don't really know much about them, or if you want to brush up on them, this is what the video is for. So today I'm taking these problems, just two problems from a University of Minnesota worksheet that I found online. So I'll leave a link in the description to that. I'm just working the first two problems. And essentially we're just finding directional derivatives. Okay, so what that is essentially we're taking the partial derivative of our function, we're going to put that in a vector, and then multiply it by this vector, which is the direction that we're taking derivative in. And so basically, yeah, and I'll walk you through the process. So let's begin. So our function is a 2-input function, natural log of the square root of x squared plus y squared. Our vector is 2, 1. And we're going to find the directional derivative with respect to that vector at 1, 0. So let's begin. First, I want to rewrite our vector as just, standard vector notation. We have 2, 1, just like that, just so we can be more comfortable working with it. So now let's begin by finding the partial derivatives. So we just have to find 2. Oops. Oh, and by the way, the notation for a partial derivative is like that. It's not a 2. It is. Some people may think it's a 2. I've seen some people that say, is that a 2? And it's not a 2, it's a del. It's an operator for partial derivatives. So, our partial derivative with respect to x, we start with using the chain rule, so it's just 1 over our function x squared plus y squared. Okay, and since we're taking a partial derivative, we're going to keep y squared constant, or y as a constant, while only dealing with x. Before we continue, I just want to make this easier for us to use. We can just raise that to the 1/2 power, so that we can just do this portion of the chain rule. So then we move the 1/2 to the front, and then we take the input. So this is a very large expression, but then we raise that to the negative 1/2 power, and this is where the holding y constant comes into play, because now we're just going to take the derivative 2x and then plus 0, because y squared is a constant in our heads basically, and so that takes care of it. So I'm just gonna erase these so that it's easier, because this 1/2 and this 2 cancel out. This is the same as that, because this is also to the negative 1/2 power, because it's a square root and it's on the bottom of the fraction. So we're taking this and we're squaring it, we're multiplying it by itself, so that it's just going to become itself. So 1 over x squared plus y squared. And then times our x, which we can't forget, so I'm just going to put that up here. Alright, so now let's take the partial derivative with respect to y. So we have del f over del y. And it's actually simple because it's the same thing, except we're holding, so like this portion is the same, since this is pretty much just like the single variable calculus part. This is the only thing that changes, because now we're holding x as a constant. So instead of 2x, we'll have a 2y. So everything else is the same, so we'll just have a y on the top. So I'm just gonna help us out a little bit and just do it like that, and that's the answer. So what are we going to do now? We're going to put them in a vector, essentially just the gradient. So the gradient of f, oops, that's a bad triangle here. It's just an upside down triangle, which is nabla, of f of x comma y. All this is the partial derivative. I'm just going to write this in this notation, and then partial derivative of y with respect to f, like that. And that's our that's all the gradient really is. And so in this case, when we have our function, so basically we'll take our function, so I'm just going to do x, y in this case. Actually no, because let's just put in the input already, so that we can do this right now, so we don't have to leave it for later. So 1, 0, so in this case, we'll take x over x squared plus y squared, and I'll plug everything in a second, and then we get y over x squared plus y squared. Okay, so now we're going to evaluate this at 1, 0. So all this is, oops, let me just make that a little clearer. So we're going to plug in 1 for x and 0 for y. So this just becomes 1 over, well, we take 1 squared plus 0 squared, so 1 squared plus 0 squared. And then we have our y, which is 0 over 1 squared plus 0 squared. So this is just 1 over 1, so which is just 1, and then here we have 0. And so that is our gradient. So now what we do is we take 1, 0 and 2, 1, and we just find the dot product. So, because all this is, I can rewrite this as just the vector dotted with our gradient. Alright, so that's all it is. So we just take the dot product. So we do 2, 1 dotted with 1, 0. Right? That just becomes 2 times 1 plus 1 times 0, which is just 2. Alright? So now we're close. We're really close to our answer. All we have to do now is just normalize the vector and find its magnitude. So the magnitude of v is just the square root of all of its components, which is just 2 squared plus 1 squared. 2 squared plus 1 squared. And that is 4 plus 1, which is square root of 5. So essentially what we're going to do now is we're going to take this, divide it by that, and so therefore our directional derivative at 1, 0 is equal to 2 over the square root of 5. That is our answer. So I'm going to do a second problem to help reinforce this idea. Alright, so our second problem here, our function is e to the x plus y z, so you can see there are 3 inputs this time, which isn't really going to make much of a difference. It's just we'll have to deal with 3 dimensions. Our directional vector is 1, negative 1, 1, so we'll write that in vector notation in a second. And then we're going to find the directional vector in the direction of, or the directional derivative in the direction of our vector d, and we're going to evaluate that at 0.111. So let's rewrite d here, just so we are more familiar with it. So d is just equal to 1, negative 1, 1. Okay, so that'll be helpful whenever we take the dot product later on. Alright, let me just write that there. Alright, so we'll take the partial derivative of each. So I'm going to start with the partial, oops, that's a bad del, partial with respect to x. I'm just going to write that like that. These are really easy because we have one of each variable, so this is just going to be e to the x. And since y and z are constant, they're just a number, they go to 0. So yeah, now we're going to do with respect to y, e to the x is a constant, y is, z is a constant, so we just take z, and then we take the derivative with respect to z, and that's just going to be, again, e to the x is a constant, and we'll just have y left over. So this is very easy, because our gradient of our function is equal to e to the x zy, so e to the x, z, and y. And so now I want to evaluate this at 1, 1, 1, so I'll just do that here. So evaluate at 1, 1, 1. So that's just going to be e to the 1 is e, and then we'll just have 1, 1. Alright, and this is our vector. So all we have to do now is dot it with 1, negative 1, 1. So I'll just do it down here. I can do this, I'll do it in blue. Why not? So we'll take, oops, maybe not. Did in red. So we have 1, -1, 1 dotted with E1, 1. Alright. And so all this is just 1 times E, which is E, -1 times 1, which is -1, and then 1 times 1, so it's just 1. So this is just going to come out to be E. And again, we have to normalize our vector. So let me do this in black again. So the thing here, alright, so all this is the square root of each of its components. Take 1 squared plus -1 squared plus 1 squared. And this just comes out to be square root of 3. Square root of 3. So our directional derivative in the direction of d of f at 1, 1, 1. Such a crazy notation there. This is just going to be e over the square root of 3. And that is it. So yeah, thank you all for watching. I'll hope to make more multivariable calc videos in the future. So hopefully you enjoy. Leave a like if you did. Thanks for watching, and I'll see you later. Bye guys.